Now we'll complete the verifiable credential flow from the verifier's perspective. The verifier requests proof, checks credentials and issuers, applies trust policy, and turns the result into access, denial, logging, and audit-ready system actions. So far, we've built the foundation: identity models, cryptographic proofs, issuers, and holder presentation flows. Now we shift to the verifier, where credentials are checked, trusted, and translated into real application decisions. In the ecosystem, the verifier is the relying party. It does not issue credentials, and it does not control the holder's wallet. Instead, it asks for the specific proof an application needs, receives a verifiable presentation, and checks whether that evidence can be trusted. That includes validating signatures, credential status, schemas, issuer trust, and policy rules. The practical output is simple: allow access, deny access, or route the case for additional review. The verifier flow begins when an application needs confidence before allowing an action. It creates a presentation request that states exactly what proof is needed, along with a challenge, domain, and expiration to prevent replay. The holder's wallet builds and returns a verifiable presentation. From there, the verifier backend checks signatures, schemas, required claims, issuer trust, revocation, and policy rules. The final response may be yes, no, pending review, or a request for stronger authentication. Think of the Verifier API as a short-lived challenge workflow. The verifier creates a presentation request with required claims, a nonce, and an expiration time. A wallet fetches that request by ID and builds the response. When the holder submits the verifiable presentation, the verifier checks signatures, schemas, issuer trust, nonce freshness, and replay risk. Clients can then poll or subscribe to status, so the application can show approved, rejected, or pending outcomes. A presentation request is the verifier's contract with the holder. It defines which credentials are acceptable, who may have issued them, and which claims must be revealed. The challenge or nonce ties the response to this exact session and blocks replay. Domain and audience binding confirm the verifier context, while expiration limits how long the request can be used. Together, these fields make the proof specific, constrained, and safe to verify. When a holder submits a verifiable presentation, treat it like any other untrusted input. Start by binding it to an active request. The request ID and challenge must match exactly. Then enforce limits on content type, size, format, and schema before deeper processing. Reject anything expired, duplicated, malformed, or unexpected. Only after proof verification succeeds should claims influence decisions. Even then, store only the minimum data needed to reduce privacy, compliance, and breach impact. Verification works best as a sequence of gates, not one big yes or no check. The verifier first parses and normalizes the presentation so the data is consistent. It then validates the presentation proof and each credential proof. Next, it resolves the issuer's DID and checks the verification method. Only after those layers pass do schema rules, revocation status, issuer trust, and application policy come into play. The final authorization decision depends on every gate passing. Begin with the presentation proof, using the holder's presentation key when the format requires it. Then verify every credential proof against the issuer's DID verification method. The mechanics vary by format: data integrity proofs, JWT signatures, linked data canonicalization, or custom proof logic. Also check challenge and domain values so an old response cannot be replayed somewhere else. Finally, enforce policy for allowed algorithms, proof purposes, and keys. A valid signature proves integrity, not trust. To verify the issuer, extract the issuer DID and resolve it through an approved DID resolver. The result is a DID document, which must contain the verification method referenced by the credential proof. That method has to be authorized for the right purpose, such as assertion. The public key is then used to check the signature. The harder questions are policy decisions. Rotated keys, historical proofs, deactivated DIDs, unsupported methods, and controller relationships can all change the outcome. Even after cryptographic proof succeeds, validation is not finished. The verifier still has to decide whether the credential means what the application expects. Match its structure and type to the VC data model and your schema. Verify required claims, formats, and allowed values. Apply time rules, including issuance, expiration, and request constraints. Then check status or revocation sources. A signed credential can still be unusable if any of these checks fail. Verification has two layers. Cryptographic checks show that the credential has not been tampered with. The signature is valid, and the issuer's key can be resolved. But that only answers. Is it technically valid? A trust framework answers the business question. Should we rely on it? It defines approved issuers, acceptable schemas, credential types, and assurance levels. So a verifier may reject a technically valid credential if it falls outside policy. Once credentials are verified, the system still needs to decide whether they satisfy the application's rules. Policy evaluation is that translation step. It can check trusted issuers, credential types, jurisdiction, age, employment status, membership level, or any other condition tied to the action. The result should be machine readable. Allow, deny, or step up with clear reasons. Keeping policies explicit and testable also prepares the system for selective disclosure and zero-knowledge predicates later. The verification result is not the final goal. It must become an authorization decision the application can enforce, allow access, deny it, or require step-up. That decision may pass through an API gateway, session service, RBAC, ABAC, or feature flag system. At the same time, record enough for auditability. Request ID, outcome, reason, timestamp, and policy version. Avoid raw credentials and unnecessary personal data, so logs support investigations without creating new risk. Verifier services turn credentials into decisions. You can now request presentations, bind challenges, verify proofs, resolve issuers, validate contents, check status, apply trust policy, and connect outcomes to authorization and audit. Next, we'll strengthen this model with selective disclosure, private presentations, and zero-knowledge tooling for production-ready VC flows.